In organic chemistry, some reactions happen much faster than expected. This phenomenon is called neighboring group participation, or NGP. Today, we will explore how sulfur atoms in halothioethers act as internal nucleophiles to accelerate reaction kinetics through a two-step mechanism. When we compare the hydrolysis of a standard alkyl halide to a halothioether, the sulfur-containing molecule reacts significantly faster. This suggests that the sulfur atom isn't just a spectator, it is actively participating in the rate-determining step of the reaction. For NGP to occur, the neighboring group must have a lone pair of electrons and be positioned geometrically to reach the electrophilic center. In halothioethers, the sulfur atom is perfectly placed to kick out the leaving group from within the molecule. The first step is an intramolecular nucleophilic substitution. The sulfur atom uses its lone pair to attack the carbon atom, displacing the chloride ion. This internal attack is much faster than an external attack because the nucleophile is already part of the molecule. This results in a cyclic intermediate called an episulfonium ion. Although three-membered rings are strained, the high nucleophilicity of sulfur makes its formation very favorable. This charged intermediate is highly reactive and susceptible to further attack by an external nucleophile. In the second step, an external nucleophile, such as water or hydroxide, attacks one of the carbons in the three-membered ring. This breaks the carbon-sulfur bond, opening the ring and neutralizing the positive charge on the sulfur atom. A key feature of NGP is the stereochemical outcome. Since two successive SN2-like inversions occur, one internal and one external, the final product often shows a total retention of the original configuration, unlike a standard SN2 reaction which results in inversion. The kinetics of this reaction are typically first order with respect to the substrate. Because the rate-determining step is the internal attack, the concentration of the external nucleophile often does not appear in the rate equation. This is known as anchimeric assistance. Consider the sulfur mustard analog. The sulfur atom facilitates the release of chloride ions, creating highly reactive episulfonium intermediates. This high reactivity is why these compounds are so toxic. They rapidly alkylate biological molecules like DNA through this NGP mechanism. Solvent choice also impacts the rate. Polar solvents help stabilize the charged episulfonium intermediate and the leaving group. In halothioether reactions, moving to a more polar solvent typically accelerates the NGP-driven hydrolysis significantly. Looking at the energy profile, we see two transition states. The first peak represents the formation of the episulfonium ion. Because the entropy loss is minimized in intramolecular reactions, the activation energy is lower than a standard intermolecular SN2 reaction. Why is sulfur so effective at NGP? Compared to oxygen, sulfur is larger, more polarizable, and less electronegative. This makes the sulfur lone pair more available to attack the carbon center, making thioethers far better at NGP than their oxygen counterparts. The distance between the sulfur and the leaving group matters. Participation is most efficient when it forms a three-membered or five-membered ring. These configurations allow for the best orbital overlap and proximity for the internal nucleophilic attack. To summarize, neighboring group participation in halothioethers leads to massive rate acceleration through anchimeric assistance. It proceeds via a cyclic episulfonium intermediate and results in the overall retention of stereochemical configuration at the reaction center. Remember these three things: sulfur acts as an internal nucleophile, the process involves two SN2 steps, and the kinetics are dominated by the formation of the three-membered ring intermediate. This distinguishes NGP from standard substitution pathways. Quick question: why does NGP result in the retention of configuration? The answer is B. The reaction consists of two successive SN2-like inversions. Inverting an inverted center returns it to its original spatial arrangement. Understanding neighboring group participation allows chemists to predict reaction rates and stereochemical outcomes in complex molecules. Thank you for joining this lesson on halothioether kinetics. Generated by Vision Solve AI.